Welcome to Cosmos for All, the show where we talk to the brightest stars in astronomy about the biggest questions in the universe. I'm your host, Christine Buckley, coming to you from the Center for Astrophysics, Harvard and Smithsonian in lovely Cambridge, Massachusetts. Today, I'm delighted to have three guests here in the studio from the Center for Astrophysics. All of our guests are involved in BHEX, the Black Hole Explorer mission, which is a new mission to discover and measure a black hole's photon ring by capturing light that has orbited a black hole. So first we have Janice Houston, who is a senior systems integration engineer at the CFA's Smithsonian Astrophysical Observatory. Janice, welcome to the show.
Hey, it's so good to be here.
Next, we have Michael Johnson, the PI of BHEX and an astronomer at the Smithsonian Astrophysical Observatory. Michael, welcome to the show today.
Thanks so much, Christine.
Finally, we have Daniel Palumbo, who is an incoming Clay Fellow. Congratulations are in order.
Thank you.
He's at Harvard's Black Hole Initiative, which is in the Faculty of Arts and Sciences. Thanks, everyone, for coming today. So the first thing I want to do is start with Michael. So you're the principal investigator of BHEX. We're going to get into the actual science of this, but I first want to take a little bit of a journey back in time. What are the first things that drew you to astronomy?
Yeah, I'm a real latecomer to astronomy. Growing up, I was really just in love with mathematics and physics, right? These are the language of the universe, and I love the idea of using them to understand everything we see, but then pushing the things that we haven't seen before. And it wasn't until grad school that I really realized that the greatest laboratories are the ones in the sky. And that's where we have all these incredibly deep unanswered questions. We can see black holes crashing together and sending shudders through space-time that we detect as ripples in the fabric of the universe, or looking at how light is bent near a black hole. So I got pulled into that in grad school and have never looked back.
Did you start out in undergrad as studying math and physics, and then when you got to grad school, you shifted over
Yeah, I never
astronomy?
took an astronomy class till grad school. I actually started teaching one to make some money and to try to impress my wife, who was studying astronomy. But I never studied astronomy.
The reasons we do the things we do, right?
Exactly.
It's a circuitous path. Opening it up to everyone else, do you remember the first time you got really excited about astronomy?
I grew up in rural Arizona, and so our night sky is really beautiful. And so I've always loved the night sky. I've always enjoyed looking at the stars. And growing up in Arizona, I decided to go to school at the University of Arizona, and I majored in astronomy and physics. And I started taking classes in astronomy when I was 16. And when I was 16, I was accepted into this program at the U of A. And it was a summer program. And during that summer, I took an astronomy class, and I met Roger Angel, who at the time was making these big, gigantic glass mirrors for the MMT. And that's really what started me on my path here.
Wow. So that's a pretty incredible opportunity to have at 16. And I guess that's one of the benefits of living in a place like Arizona.
That is correct. Having access to a Research One school, and at the time the school was known for astronomy, especially its graduate program, and also the state was committed to providing education to its high-performing students, and so I was able to go to the University of Arizona on a scholarship, and that really changed everything for me.
That's so cool. Daniel, what about you?
Yeah, so I guess in high school, I definitely considered myself on the path to becoming a theorist. I really wanted to do physics in college. And somewhat by coincidence, I ended up going to a summer camp called the Summer Science Program, which is very generic sounding, but it's an astronomy camp. I grew up in Los Angeles, so I had very little access to the night sky as a kid. I also have terrible vision, so I never did much stargazing. But at the summer camp, it's very hands-on, very observational. You are assigned one near-Earth asteroid to take charge of and do a very old-fashioned orbital determination for. And for me, I'd never considered doing observational work of any kind, but the intimacy and the toil of just being up all night and looking at one specific object that is yours for that summer, I really fell in love with that. I was a night owl already, but
I was going to say, you must have liked that part too.
Absolutely, yeah. I mean, to me, that really planted the seed of astronomy in my brain, and then later in undergrad, I started to get involved in, I guess, the very early days of imaging with the Event Horizon Telescope, and the rest is history.
Is it a benefit to be a night owl if you're an astronomer?
Less so than I hoped. There's a lot of 8 a.m. and 9 a.m.
Janice shaking her head.
Yeah.
I guess astronomy happens all over the world at any time of day, right?
Yeah.
So I sensed a theme here that you all had educational experiences that sort of launched you into, no pun intended, launched you into this career. How did you get around to coming back to the idea of black holes?
Well, for me, I think the EHT image of M87 is really the most consequential image of this century in astronomy. And so that is the reason why I joined SAO, was because that image did inspire me. And then luckily I met Michael Johnson, and then he convinced me to join the BHEX team. But prior to that, I would never have wanted to do another mission again.
Yeah, our understanding of the universe stops at the event horizon of a black hole in a lot of deep ways. And the fact that we can go look at those edges of all we know, to reuse the title of a documentary about the EHT, is very special. It's not every day that you can go look at something you don't understand and try to make inferences about it. So to me, it's just such an obvious thing to do. If you have a few of these sitting around, you ought to go look at them and try to understand them more deeply. And yeah, so to me, we have a handful of black holes which are really big on the sky, and it's a natural use of one's life to try to understand these things in gory detail. That's the hope.
We know that our theories of physics are incomplete, and they break down at the edge of a black hole. And so chasing fundamental understanding and fundamental knowledge, that's the place we want to look. When we see the image of a black hole, we're staring right at something we don't understand. And every impulse we have is to chase that, and to do whatever it takes to push our theories there and to push our experiments and to see where they merge and what we can learn from it.
What's interesting to me, though, I have a slightly different perspective than the theorists, which is, to me, this is a very difficult measurement. And to be able to make the instrumentation that can make the measurement is what is interesting to me.
The instrumentation is so highly detailed. Everything has to go exactly right.
It's not an instantaneous gratification thing whatsoever. So on my last mission, I did not feel like I succeeded until 2 years after it was in orbit.
Oh, wow. So after it had already launched.
After it had already launched. And that was because they finally got the result that they were looking for.
Yeah.
So you just have to be patient, and you have to be patient with the fact that it's a long road, and you're not necessarily on the road the entire mission either. You may have to fork off the road, but the road's continuing, and then you can kind of catch up to where the end point is later on.
I've been trying to talk to my 2 young children about black holes, and they say things to me like, if we can't go inside, how do we know that there's anything in there? And then one of them said to me the other day, that makes me feel really tiny.
It's strange, right? There's a mix of this sort of depersonalization and this vastness in which you are lost when you look into space. But on the other hand, there are a very small number of these black holes that we really get to know in detail like this. There aren't that many people who look at them. It'd just be one of a handful that really just spends years or even decades trying to understand the intricacies of one of these objects. I think there is a sort of personal nature to that, and also sharing in that work with so many other talented people. I think it's actually very heartwarming in some sense, and that vastness does not feel surmountable, but is at least something you get to share in with others, and so it's not a cold feeling.
I love the hugeness of what we study. I love that astronomers can argue over the age of the universe, right? I love that our mind lets us explore these things that are unthinkably vast compared to our daily experience. And I think that's what makes it worthwhile to spend years or decades of your life in pursuit of this. It's what Janice was saying, that it's because it's hard, and it's because it's not just a hard task that anyone can do. You think you have the right mix of the organization and the people and the team to do this for the first time in human history. Your effort is important. It's so special to have such a sharp goal associated with the ability to work hard and know that at the end you'll be able to achieve it because of that hard work.
I think it's also interesting that it seems like in a lot of science fields, some of the biggest unanswered questions are some of the most central ones.
I think black holes are just so central to the biggest questions about the universe. And is it possible for singularities to exist in nature? Are there holes in the universe? Are there these infinite wells of gravity in the universe? And what does that even mean? It's just tantalizing, right? How can you not think about them?
Do you want to talk in a little bit more detail about what the Black Hole Explorer is, what the big questions are that you're trying to answer with this mission?
Yeah, this is a radio telescope that we want to launch into space. And after doing that, it's going to link together with radio telescopes all over the world. And that's going to create a virtual telescope 3 times the size of our planet. This is going to produce the sharpest images in the history of astronomy. And they're sharp enough that we can zoom in on black holes and we can see light that's actually orbited around the black hole before escaping. That's this feature on black hole images called the photon ring. So really it's a goal to journey right to the edge of a black hole and to be able to study the light that has danced right around the edge of the universe before only barely escaping the gravitational pull of the black hole to escape with the secrets of the black hole imprinted on it.
What's important about being able to get that higher resolution of the light? What is it going to tell us?
Yeah, so near a black hole, it's actually a very complex environment. There's a hot plasma. It's 100 billion degrees. It's swirling around the black hole. It's very complex. And what we want to do is isolate the space-time of the black hole from all the complexity of the surrounding astrophysics. And the beautiful thing about the photon ring is that light, as it's moving through all this complexity, doesn't care at all. The photons are deflected something like 1 billion times more by the gravity of the black hole than by all this surrounding material. So they're this wonderful tracer that just pierces all of that complexity, and the way that the black hole moves the photons and lenses them and shapes how they're passing through the space-time, that's what tells us in a very precise way exactly what the black hole's properties are. We think astrophysical black holes only have 2 properties. One is how much mass they have, how big they are, how much they've consumed as they were formed. And the second is how fast they're rotating. And we now have lots of ways in astronomy of studying exactly how big black holes are. But the incredible thing is that we still don't know whether or not these supermassive black holes at the centers of galaxies are spinning. And this is tied to some of the biggest questions.
Oh, wow. You hear people talking about tiny black holes and then huge supermassive ones. Is that the range of size that we see?
There's no smallest black hole, there's no biggest black hole. At least there's no limit in nature. And so now through the EHG, we've seen black holes that have something like 6 billion times as much mass as our sun. It's incredibly massive. And we think that there are millions of black holes floating around the Milky Way that are much, much smaller.
Millions just in the Milky Way?
Just in the
Wow,
Milky Way.
okay, yeah. That's a lot.
Exactly. And there could be much smaller ones too that could even evaporate in a little burst of Hawking radiation. So people have looked for those for decades and decades. But the short answer is we just don't know. Black holes are very good at hiding, which is why it's so incredible that these ones at the centers of galaxies, we know exactly where to look to be able to zoom in and see what they're made of.
Yeah. Dana, I'm going to pick on you. Can you talk a little bit about what your role is in the project?
Sure, yeah. Within the Black Hole Explorer mission, I wear a couple of hats. One of them is the simulations lead, which is to say, making sure that with our current understanding of instrument projections and our current understanding of our targets, we are delivering the science that we think will truly be transformative to the field of black hole astrophysics and really fundamental physics. I'm also a co-lead of the photon ring science working group of the Black Hole Explorer mission. So I work specifically on how we're going to understand the signatures of lensed light as they appear in our data, and how we'll measure things like mass and spin in practice. So the sort of nitty-gritty details of how we will do that measurement.
You talked about the working on simulations.
Yeah.
How does that work when you haven't launched it, you're not actually collecting data yet, but you know what kind of data you're going to get and you're running simulations to be able to make sure you can process it in the right way?
So a big part of launching a space mission is knowing what you need and what you want and how that will appear in a practical sense. And the better you can simulate it, the better you'll be able to perform when it comes time to launch. So a lot of my work has been building a simulation pipeline end-to-end that will model how BHEX will perform and how that data will be utilized for science.
And Janice, you're the engineering guru. Tell us about what your role is in BHEX.
So I have 2 roles.
Okay.
The first role is I'm the project systems engineer, which means I'm the lead engineer for the entire mission. And then my second role is to specifically be the instrument systems engineer, which is to be the engineer for the instrument. And the difference between the roles is as the instrument system engineer, I'm responsible for delivering the instrument. And as the project systems engineer, I'm responsible for the whole mission, which is making sure that the instrument is integrated into the spacecraft to make an observatory, to make sure the observatory fits into the launch vehicle, to make sure that the launch vehicle puts the observatory in the right orbit, and to make sure that we're in the right orbit such that our communications on the spacecraft can downlink to the right data centers on the ground so that the scientists eventually get the data that they need so Daniel can actually do the work that he needs to do on that.
That sounds simple. That sounds like a very easy job. Maybe walk us through what each of those things are and what they look like, what they're going to be when BHEX launches.
Sure. So the instrument is actually the radio telescope. So the instrument includes an antenna, 3.4 meters in diameter. It includes a receiver that can simultaneously observe at a couple of frequencies that are high frequencies. And it includes a data processor that can digitize this large data volume, and it includes an optical downlink laser communications that will actually is paradigm shifting for missions, which will be able to downlink this large volume of science data from our instrument to our ground optical terminal, and which will then relay it to the Science Operations Center.
And that's no small feat.
That
right?
in itself is no small feat.
Yeah.
Then what the spacecraft does is the spacecraft accommodates the instrument. It provides thermal management, it provides attitude control, and it provides communication back to the ground to receive commands and to relay the spacecraft housekeeping data. And that's really the purpose of our spacecraft. And then together, the spacecraft and the instrument make the observatory.
So maybe we could talk now about this data downlink test that you did.
So one of the things that's really critical to BHEX is our ability to downlink this large science data volume. And Michael and Daniel will tell us all the facts of how large it is. But what's really important for us is that we are going to be able to take use of technology that has been proven in some other missions and some other experiments that have been performed on space and actually implement it for science usage. And our partners at MIT Lincoln Labs have been developing this technology for quite a while, for the past 10 years or so, and have demonstrated successfully this technology. So last fall, we basically emulated the radio telescope through the optical communication system and basically created a virtual space radio telescope and a virtual ground radio telescope, sent signals through both of those paths, and then the scientists did their correlation and analysis on that data. I'm handing it over to you, Daniel, for the rest of it.
Yeah, so I guess just taking a step back for a moment, a key enabler of doing this mission at all is the high data rate. We are trying to gulp down as much of a sort of broad spectrum emitter as we can to eke as much signal to noise as we can out of the signal that we're getting from a supermassive black hole. And at the bandwidths that we would normally be operating on for a similar dish on the ground, that would be impossible to pull down from space without using lasers to beam that information down. And so for us, this went from being totally impossible to being routine or in a matter of just a few years. And that's why we're striking while the iron is hot in some sense.
How did that happen? Is that because of the technology that has been developed at Lincoln Labs that was...
Yeah, that's
that
right.
was able to happen.
Some key sort of technology demonstrating missions that have made this possible, and we expect it will be the future.
So how big is this data? What's the, do you have a way that the average person can understand?
Yeah, so
the bigness.
It's about 100 gigabits per second, which is faster than the internet you will typically get at your home, right?
It's 1,000 times faster. I mean, it's unthinkable amounts of data that you're sending down in a laser beam. It's amazing that this is possible. And so the way it's going to work is that BHEX will point at a target, and it'll point a second downlink telescope at the Earth. And so it's going to be streaming, it's going to be collecting all these photons from the black hole. We can convert those into a digital signal, into a bunch of bits, and then we dump it straight to ground as fast as we can. And so that's these kind of ludicrous data rates that Daniel's talking about. And to put it in context, in the EHC, we were literally shipping around truckloads of hard drives, like huge amounts of data.
Yeah.
And so the fact that you can do this with actually a pretty small laser terminal from space, 20,000 kilometers from the Earth, it's just marvelous. You can just do incredible things with these data rates for science that we're only beginning to explore.
What's the timeline looking like right now?
So right now we're in the proposal stage. And so that means the team is developing the mission concept, and we're developing physical hardware along the way to demonstrate that we can actually do this. And then when we are selected as a mission, launch is usually 5 to 6 years after mission selection. So we're really targeting early 2030s to be on orbit, and then we're going to collect data for 2 years. and then the mission will end, and hopefully within a very short time, the scientists will have the image of the photon ring. I'm kind of hoping that they're wrong and the image looks slightly different, but we'll see what happens.
Tell me more about that. What's
What's
behind that?
What I like about missions, like in my last mission, scientists always have a theory, and it's always kind of interesting when they get unexpected data, because then they become very curious about what does this data mean, and it makes them have to challenge their hypothesis, and then they get together, and then they argue, and then they come to a conclusion. And that's also fun in the process, to see that they have to re-challenge themselves.
Mm-hmm. How many people are involved in the mission?
I'd say we're in the high 50s, and by the time we launch, we'll be in the low thousands.
Oh, wow. So that's many people who are going to be looking at the same, or using this data to look at different things, right? Lots and lots of different questions being asked, all about black holes, but all sorts of different questions, right?
Yeah,
Daniel.
The team is nimble and sharp, but it's worth noting we also have this huge community of scientists who are incredibly excited about what BHEX will reveal. And we occasionally have broader science meetings where we welcome in this huge cohort of, in large part, theorists, people who study black holes and gravity, who have questions which can only be answered by BHEX. And I think there's a statistic which Michael probably has off the top of his head for number of papers written about the photon ring over the last few years. It's an exploding community of people who are just waiting for these razor sharp images of these black holes to understand the cosmos in a new way.
Yeah, rule of thumb, every day someone writes a new paper on the photon ring. This is for something that 10 years ago we didn't know we'd ever be able to see. And most of these people we've never met, right?
Yeah.
So I think that's what's so exciting, is being able to create this new data that lets us see something that's never been seen before, and have a whole set of people all across the globe, some close and collaborators that we talk to every day, and some who we've never met, and some of the scientists who are in middle school now who are going to be doing data analysis when the mission launches. And that's just part of the fun of it.
Is this the kind of mission where you really just want a lot of people joining and using the data in whatever way they can?
Yeah, a big part of our philosophy is that the data should be freely available. We're going to release everything publicly as soon as possible, ideally days after we produce that data. And we want everyone to be able to look at it. I want high schoolers to be able to download our scripts and see black hole images themselves. And something really exciting about the photon ring is it produces a very particular signal for BHEX to see. My hope is that we'll actually see that sort of coming into focus shortly after launch as the data is being taken, and that everyone can be part of that discovery process. It's very much something we want to share.
It's been the most exciting point so far for each of you.
I guess coming from the simulation side, as we've gotten a better and better understanding of how the BHEX spacecraft will perform coming into clarity, it's going to be transformative. It's just night and day. I think we're going to learn more than we expect, and we already expect a great deal. So I'm just terrifically excited from seeing our internal projections, and now what many of our students are working on and publishing is demonstrating that BHEX is going to reveal black holes in a way that we wouldn't have dreamed of 10 or 15 years ago.
Yeah.
I think the engineering team is really excited about being the bridge basically between the science and the engineering to make this happen. And that it's important to realize that this is a global project. And so when I said thousands of people will touch this, it's because there are so many different skill sets that are needed. People who contribute to this type of mission have specialties in mechanical design, or because of the high data rates, and because this is radio astronomy, there's a great need for RF engineers and electrical engineers, and people who are interested in optical downlink terminology, people who run the ground infrastructure to receive spacecraft commands, and people who write software to do spacecraft commands, and people who do mission operations, and people who do science operations, and people who study materials and properties, because we have to have certain types of materials on the spacecraft and certain types of materials on the instrumentation. Contamination experts, people who are good at building launch vehicles. So from my standpoint, it's a huge community of engineers that make this mission possible. I always like to see the scientists when they're in a clean room and they see somebody else's spaceflight hardware because they get all excited and giddy. And it's a nice reminder because I've been doing this for over 30 years and I'm used to being in a clean room and seeing hardware. So it's nice to be in there with for somebody who's always a new experience. This is my career and it's been a great experience, but it's always nice to be with somebody who just finds the absolute joy in it again.
Do you have colleagues who you're like, that person's really into it, they get the most joy?
It's
Janice?
totally Michael. It's hard to picture Michael now, but he's very tall and he has very big feet. So none of the clean room garb also fits him either. So that's always fun too.
Do you feel, I guess you feel the spectrum. So Janice is saying you exude joy, but then there's also terror. Must be swinging back and forth from a lot of different emotions. And
Yeah, but
working on something like this.
Janice said she never thought she would do another space mission. But then you see, once you work with these people, they just can't escape it, right? These are the adrenaline junkies of the science world. And the joy and the trauma and the pain and the excitement and the mix of it all, I just don't see how you could do anything else after getting involved with this. And I think maybe Janice sees the joy that I have as I'm in the clean room. But I just see that across the whole science team of people who are so hungry for discovery and for understanding, and seeing that we're on the cusp of that. It's just palpable and so exciting.
In terms of things that have surprised me, there are an enormous number of students, undergraduate and graduate, who are extremely excited to work on this mission that may not launch until after they graduate. I've been blown away by the amount of students who are super excited to commit a decent chunk of their youth to making this real. And in large part, it's because they were inspired in middle school or high school or early college by seeing the Event Horizon Telescope image of M87. And so they saw that and they wanted more. And they plan ahead. They come to us and they say, this is what drives me. Let me be a part of this. I want to help make this real. And this cycle will continue. And BHEX is going to reveal these black holes in new detail, and it will be newly inspiring to a new generation. And I think that story of continual discovery and learning more and more about black holes, while also bringing in so much young talent, it's a beautiful thing to be a part of.
Is there media, books, movies that you think treats black holes in a good way?
Look, Matthew McConaughey has the best track record in astronomy movies. He did Contact and Interstellar.
I do think Interstellar is fabulous.
Yeah.
If you just want to viscerally experience the paradox of clocks changing near a black hole or space-time being warped, it does such a lovely job.
If I have to throw in an oddball now that Interstellar has been taken, I think the oddball I would throw in, there's a game called Outer Wilds, which takes a very sort of micro clockwork view of being and living near black holes and interacting with them as mechanical objects that are a piece of the functioning of the universe. And I found it just tremendously compelling and would strongly recommend it.
Is it a video game?
It's
or
a video game, that's
okay,
right.
yeah.
But it's very much a sort of thinky, puzzly type affair.
In 30 years, after BHEX has even hopefully come and gone and we're on to the next black hole mission, what do you hope that we know about black holes that we don't know now? And what do you hope we're working on trying to find out next?
Well, I think BHEX will teach us to a sharp degree whether GR is right at the order that we can probe with spin measurement. Right? If we see photon rings that are consistent with our understanding of general relativity and consistent with our understanding of how spin warps the space-time, then that's great. That's another test that Einstein's general relativity will have passed. But there's room for surprises there. And as theory marches on while we watch BHEX and think about these images, there may be new surprises, new subtleties in quantum gravity that emerge, things for us to look for in these images. I would love to have a much sharper understanding of deviations from general relativity that we can seek in images.
I think for me, one of the big mysteries in the last century was quasars, right? Active galactic nuclei. And it took decades for people to realize it, but we now know that these are sources with a black hole right at the center of a galaxy, and they can be putting out more energy than all the stars in the galaxy combined. And it's still very much a mystery of how that's possible. But the theory is that you have a spinning black hole, and these bright jets coming from the heart of the galaxy are actually drawing away spin energy. They're siphoning energy from the black hole itself. And to me, that's just such a deep, paradoxical, wonderful property. And it's the kind of thing where you want to see it in action, right? You want to see black holes being twisted by these magnetic fields to be absolutely sure. And that's the thing that on a 30-year timescale, I think it's possible. And it would shatter our expectations for how black holes can interact in nature.
What kind of things are great about working here at CFA to do a mission like this?
The magic of the CFA is you're just surrounded by experts, and you can walk down the hall and meet someone who has an incredibly deep understanding of either exactly the problem you're working on or a topic you didn't even know that existed. I think the centralization and concentration of so much expertise and people who are so generous with their time and wisdom and knowledge, it's just such an inspiring place to work. And it's something where I think everyone who passes through here emerges with a much broader understanding of astronomy and astrophysics and more ambition about the kinds of things they can study.
At one of the new employee orientations, you were involved, and I was floored at the earnestness with which you got up to the mic and looked around the room and said, "This is the time of your life. You're never going to work any place like this ever again." It sounds like you really believe that.
Oh, no. I still remember setting a foot in Cambridge for the first time. And I was here for a job interview for a postdoc. And I thought, there's no way I'm going to get a job here. But just to have walked around, what a gift, right?
Yeah.
It just felt like a sacred place that I was so happy to just come and be here for a moment. So I don't know, there is something to it. There's something in the air here that just makes it so vibrant and special.
Yeah. What would you say to a young person who maybe is in high school or, I don't know, middle school now, who's looking at the stars, maybe in Arizona, thinking about, wow, this is so cool. I want to do this with my life.
Something I emphasize to students, especially students who are facing imposter syndrome or just any sort of self-doubt or wondering what their place in astronomy is or what their place in a big mission like BHEX is that astronomy, especially in the modern era, takes many hands, many eyes, and many minds and many ways of looking at the world and looking at hard problems. I remember going through horrendous periods of self-doubt where I thought, this one part of this problem just seems totally intractable to me. What am I doing here? Really, it's just a mission like BHEX touches on so many pieces of human ingenuity, from engineering to theory to observation to how we actually build things physically in the lab, to how we conceptualize the cosmos and our ability to predict weather. I mean, if you are passionate about helping advance human knowledge of the universe and our role in it, no matter what your talents, no matter what path you've taken, there is always a way for you to help and to move the ball down the field. And really the passion that will take you there, and there are winding paths, especially in this day and age, that will take you there. The way I see it is, just follow your heart. You will find your place working on something you love.
Janice Houston, Daniel Palumbo, Michael Johnson, thank you so much for coming on to the CFA podcast and talking about BHEX. It was really great to have you.
Thanks so much.
Thanks for
Thank
having
you.
us.
Great to be here.